Alright, so yesterday we talked about ionic bonding, which is metals with nonmetals. The metals lose electrons, become cations, nonmetals become anions. And then at the end we talked about how covalent bonding is with nonmetals, and they make single, double, or triple bonds. Well, today we're going to talk about how Lewis structures are formed. Or how you draw them. Lewis structures are drawing a molecule or an ion which makes covalent bonds. If they make covalent bonds, then we're going to determine if they make single, double, or triple covalent bonds. We're going to take two examples and go through all these steps which are on your PowerPoint note sheet, and we'll go through two examples. First of all, I want to count the number of valence electrons for all the atoms. So I went to the example of methane, CH4, and water, which is H2O. We'll look at my periodic table. Carbon has 4 valence electrons. Hydrogen has 1 valence electron, but 4 atoms. So I'm going to take 4 times 1 of 8 valence electrons for methane. For the water, I get 2 times 1 for the hydrogen, plus 6 more for the oxygen, for a total of 8 valence electrons again. This is not always the case, but it just happens to be with these first two examples that I'm doing. The next step is to put the least electronegative atom in the center. And while that's often going to be the case, we're just going to put the one that's by itself in the middle every time. I'm just going to draw those right now. Carbon's by itself, so it'll go in the middle. And with the water, oxygen's by itself, so it will go in the middle. So, just taking that next step, all I'm doing is putting the one that's by itself in the middle, and the other atoms around it. Next step. I'm going to join the other atoms to the central atom using one pair. We're always going to assume a single bond to start with. So this is where I just left off with. So I'm going to assume a single bond on this. And then the water, I'm going to assume a single bond to start with. So that is that step, creating a bonding pair or a single bond between each of these atoms. Now, we'll use the remaining electrons. You might say, what remaining electrons? Well, for CH4, we said that there is 8 valence electrons. And we have C with these hydrogens around it. Single bond, single bond, single bond, single bond. And then for the water, we also said that there's 8 valence electrons. And right now we have single bonds to the hydrogens, and that's where we left off. Well, in the case of methane, we already are using 8. The hydrogen is already stable because it has 2, because it's now like helium. And carbon has 8 around it, which most atoms will need 8 according to the octet rule. So everything's stable here, and we equal 8 valence electrons that we counted in the beginning, so we're good. This Lewis structure is done. But this one's not. We need 8 when we're done. We only have 4. The hydrogens are stable with 2 each, but the oxygen's not. It needs 8 total. So we'll put 2 here and 2 here. That fulfills its octet rule. That gives me 8 total, and it causes everything to have the correct number of electrons. So that is a completed Lewis structure for water. What if it doesn't work out that well? Well, I'll give you an example. Carbon monoxide is a good example of one that will not work out right away. We count out the electrons. There's 4 from carbon plus 6 from oxygen. That gives me 10 valence electrons that my final Lewis structure must have. If I just set them up next to each other, because that's the only way two atoms can bond, and assume a single bond, and then I try to use the rest of my 10 to give 8 to each of them. I go 2, 4, 6, 8, 10. At this point, I'm out of valence electrons. So I cannot give oxygen its 4 more, which it needs. So what I'm going to do is change that single bond to a double bond. And by doing that, I take 2 off of that carbon, so it gives me 8 for the carbon and 6 for the oxygen. I have 2, 4, 6, 8, 10. So my problem is still that oxygen does not have its 8. So what I can do in this case is change this to a triple bond, which will allow me to remove a set of electrons from carbon. Put this other set on the other side. That gives me 10 total valence electrons. Carbon has its 8, oxygen has its 8, and that's the correct Lewis structure for carbon monoxide. So that is a possibility, and you just need to change into double or single, triple bonds depending on what works. What are some of all the exceptions? Okay, hydrogen we already said is okay with 2 valence electrons, so it's stable with 2 valence electrons. That makes it like helium. Beryllium is kind of an interesting thing. Beryllium is an alkaline earth metal with 2 valence electrons. If it bonds to, say, 2 hydrogens, it is stable. So it is stable with 4 valence electrons. Boron has 3 valence electrons, same type of thing. If it bonds to 3 hydrogens, it is stable with 6 valence electrons. So there are some exceptions to the octet rule. Everything else, so that's what this is, exceptions to the octet rule. All the other atoms we'd expect when we are done with the Lewis structure to have 8 valence electrons when done. Phosphorus and sulfur can each have an expanded octet with 10 or 12 valence electrons. So an example of that would be pH 5. If I count up the valence electrons, there's 5 from the phosphorus, 1 from each of the hydrogens, for a total of 10. If I put I'm going to go up here now, if I put the phosphorus in the middle and the hydrogens around it, single bond them, hydrogens are good with their 2. Phosphorus now has 10, which is not following the octet rule, but it's an exception and is now stable. So that is just fine. Alright, what about ions? Well, ions are a little different. Polyatomic ions are held together with covalent bonds. So this is a polyatomic ion known as hydroxide. It is held together with covalent bonds. So that means just oxygen and hydrogen are bonded together with covalent bonds. Same rules. I have 6 valence electrons plus 1 from the hydrogen, which equals 7. But this negative one charge indicates that I have 1 more valence electron. So my final Lewis structure is going to have 8 valence electrons. So that is the one difference here. I need to add or subtract. If this was a plus 2, I would have to take 2 electrons away, because whenever I have a minus 1 charge, that means I have 1 extra electron compared to normal. So I do my same thing, single bond, assume that hydrogen's now complete, 2, 4, 6, and the 8 that were here. And ions are always put a brackets around it with the final charge on the outside of it. So this is the whole Lewis structure for hydroxide. So it is a polyatomic ion in which you have 2 or more atoms combined, and that whole group of atoms has a charge to it. Let's do one more that's on your Lewis structure sheet. It is NO3, 1 minus. If I count the valence electrons, I have 5 from the nitrogen, plus 18 from the oxygens, because there's 3 with 6 each. That gives me 23. Since it's a 1 minus charge, I'm going to add 1 to that total. So my final Lewis structure would have 24 valence electrons. As I put nitrogen in the middle and oxygen around it, assume single bonds, I have enough electrons to get me to this point. The problem is nitrogen does not have 8. So that means I'm going to have to add a double bond somewhere. I'm going to pick right here. When I do that, I can erase these 2 electrons. Now every atom has 8, and you have 1 minus charge. This would be a case which would show resonance. Resonance is the idea that there is not just one Lewis structure which defines a molecule or ion, because we just picked that left oxygen to get the double bond. In reality, it could be the right oxygen, like I am showing here. Right? So that is another valid Lewis structure. Another valid Lewis structure would be the top oxygen to have the double bond. So there are three valid Lewis structures, and resonance happens when you have more than one possible structure, possible place for that double bond, and you just pick one of the places, but in reality there's more than one place. As far as these bonds go, this double bond and this single bond, all of these bonds are identical, and none of them are actually single or double. They are between a single and double bond. They're all identical, and they're between a single and double bond. So this is our best way to show for this ion what it looks like, but it is a limitation to Lewis structures, because in reality it is not two single and one double. All these bonds are identical, and it is somewhere between a single and a double. A little closer to a single as far as bond length. Single bonds are longer than double bonds, which are shorter. Triple bonds are shorter still. So it would be a little closer to a single bond as far as bond length goes, but it would not be a single bond. It would be somewhere in between. So that is Lewis structures. What we do at this point is a bunch of practice on Lewis structures.